And so today we are going to exploit the Feynman integral trick in order to obtain the value of the integral between 0 and pi by 2 of x upon tan x. And so I've written the integral at the top left hand corner there, and on the right hand side I'm doing some substitution. U equals tan x, du by dx equals sec squared x, which is tan squared x plus 1, which is u squared plus 1. So du by dx equals u squared plus 1, which means that dx equals du upon u squared plus 1. And of course x equals arctan u. And so if we look at the second integral I've written in the middle of the screen, our integral is now the integral between 0 and infinity of arctan u du over u, which was tan x, and then u squared plus 1, so that we now have du over u squared plus 1, replacing dx. The limits, the bottom limit was 0, the tangent of 0 is 0, the top limit was pi by 2, and the tangent of pi by 2 is infinity. And I now choose the parameter for the Feynman trick, which strictly speaking should be the Leibnitz trick. The integral of t is not arctan u, it's arctan tu du over u squared plus 1, and so I've written the t version of the integral there, and now we are ready to do the partial differentiation. And so if you look on the left hand side, I've produced the integral of t, where I've placed the Feynman parameter there, and we should bear in mind that what we're aiming for is the integral of 1. So on the right hand side I've written the same integral without the t there, so that's arctan 1 times u instead of t times u on the right hand side. And so what we're going to do now is to take the partial derivative with respect to t of the integral, do the integration, and then integrate once again in order to find the value of the integral. And now I complete my partial differentiation of the integral in terms of t. So y equals arctan tu, tan y equals tu, differentiate both sides with respect to t, divide by dt, sec squared y equals u. Sec squared y is tan squared y plus 1, which is u squared t squared plus 1. So divide by dt is u upon u squared t squared plus 1. And that is the derivative of arctan tu. And so here at the bottom right hand corner I have my partially differentiated integral with respect to t, which becomes u du on the top and u squared plus 1 over u squared t squared plus 1 on the bottom, and we find that the u's cancel, and so we can now have a simpler integral. And so this is my simpler integral, I primed of t, between the limits of 0 and infinity. And so what I now have to do is to sort this out in terms of partial fractions, which I must do in terms of u, because I'm integrating with respect to u. And so if we look at the partial fractions calculation, we eventually see that 1 equals pu plus q, all multiplied by u squared t squared plus 1, plus ru plus s, all multiplied by u squared plus 1. And if we compare the coefficients of u to the 0, 1 equals q plus s. And if we compare the coefficients of u squared, 0 equals qt squared plus s. And if we look on the right hand side, where we substitute q equals 1 minus s, 0 equals 1 minus st squared plus s, which eventually leads us to the conclusion that s equals t squared over t squared minus 1, and q will be 1 minus that. And so if you look at the bottom left hand corner, in black we find that q equals minus 1 over t squared minus 1. So I'll now summarize that at the top of the screen, find out the values of P and R, and we'll go from there. And so if we compare the coefficients of u cubed and u to the power of 1, we find that 0 equals pt squared plus r, and that 0 equals p plus r, so that r equals minus p. And eventually we find that 0 equals p times t squared minus 1, which can only be true if p equals 0. So p equals r equals 0. And we're now in a position to compose our partial fractions and to do our integration. And so I split that up into the integral between 0 and infinity of 1 over 1 minus t squared times 1 over u squared plus 1 du, minus the integral between 0 and infinity of t squared du over 1 minus t squared u squared t squared plus 1. And I deal with the one on the left-hand side first, which is quite straightforward. It is 1 over t squared times arctan u taken between the limits of 0 and infinity. And eventually we find that is 1 over 1 minus t squared times pi by 2. And I now deal with the other integral, which is just a little bit more complicated. So I integrate this. A equals ut dA equals dA by du equals t dA upon t equals du. So my new integral is 1 upon a squared plus 1 dA upon t, which is 1 upon t arc tan A. And if I put in the limits, that is 1 upon t pi by 2 minus 0, which is 1 upon t pi by 2. And so my integral as a whole becomes 1 upon 1 minus t squared pi by 2 minus 1 upon t squared upon 1 minus t squared pi by 2. So I'll write a neater version of that for you in a moment. So if we look at my neater version at the top here, we have 1 upon 1 minus t squared times pi by 2 minus 1 upon t squared 1 minus t squared pi by 2. And if I tidy that up a bit and factorize, I find that I primed of t is pi upon 2 lots of 1 plus t, and the integral of that is pi upon 2 times natural logarithm 1 plus t plus c, and so now we have to find the constant of integration. So if we look on the right-hand side, we remind ourselves that I of t is the integral between 0 and the infinity of arctan tu upon u times u squared plus 1 du. And so I now put 0 in where the t goes to find I of 0. And so we find that the integral of 0 is 0. And so I can now put this in on the bottom left-hand corner to find the constant of integration. So that 0 will equal to pi by 2 times the natural logarithm of 1 plus 0 plus c. I'm sure that's not very neat. And so we discover that 0 is pi by 2 times ln 1 plus c, so that 0 equals 0 plus c, so that c equals 0. And we bear in mind now that what we wanted was I of 1, where we have I of t at the moment, so I of 1 is where the t equals 1. And so the answer to our question is that I of 1, and so if we put the 1 in where the t goes, we find that our final answer is pi by 2 ln 2.